Welcome. We now continue on looking at work and energy and have looked specifically as work as a change in energy. So last lesson we had a look and we found that work is defined as a force acting through a displacement. We also found out that work is any change in energy. So also work is a change in kinetic energy, and it's also a change in gravitational potential energy. So having a look at this diagram here, we see a small cart which is initially at rest, and it is then made to move by a force. Now this force that is acting on the object doesn't just act instantaneously for an infinitely small amount of time. It actually has to be physically present on this cart. And as a result, because the hand is in contact with the cart will move through a displacement while the force is operational. In that case, I have a force and I have a displacement, therefore work is done. And we know that as this happens, the car must accelerate, because this is the condition of a mass being displaced through a displacement, but that mass with a force must cause acceleration. So an acceleration means we've increased our velocity. If we've increased our velocity, we must have changed kinetic energy. So that's the reason why we define work as a change in kinetic energy. The second diagram below has a weightlifter lifting a barbell above his head, and it's through a displacement of h here. Okay, we're going through a displacement of h. Now this is just a vertical displacement, so it's still an s, and the minimum amount of the minimum amount of force he needs to lift with is got to be greater than the weight of these barbells. Now these barbells together would have a weight, and if he didn't lift any with his arms, didn't lift more than that weight, then he would not be able to move the barbell up at all. So the minimum amount of force that he needs to supply is mg. So mg, that's the force multiplied by the displacement. He would need to give me mg times delta h, which is the displacement. And we're going to define that as the change in gravitational potential energy, because here he's put work into it. Remember, he must be doing work, and work is the change of energy, so it's force times displacement, and that means he's put energy into this system of barbells. If he was to let go, the barbell would drop, and that energy would be released back as kinetic energy. So this must be, him raising this must be a change in potential energy, and therefore it is a change in U, and work is therefore defined as also a change in gravitational potential energy. So having a look at the formula that we introduced to ourselves last lesson, this is the formula for kinetic energy. Kinetic energy is a half mv squared. We should commit this to memory because it is one of the most famous formulas of all time. So mass must be measured in kilograms, velocity must be meters per second, and that would give us joules in, kinetic energy in joules there. So we have a quick question underneath. A car has a mass of 1,200 kilograms, and it's traveling at 90 kilometers per hour. We're going to calculate its kinetic energy. So if we want to calculate kinetic energy, just simply calculate the kinetic energy, we use the kinetic energy formula. But remembering, we must have this velocity in meters per second. So multiplying that, remembering to go from kilometers per hour to meters per second, we want to multiply by 5/18. So 90 times 5/18 is 25 meters per second. So this is 25 meters per second. Okay, please don't add kilometers per hour into the velocity formula. It just will not work. So our kinetic energy would equal a half times 1200. That's the mass times 25 squared. All we need to do is complete that multiplication. And unless I've got fat fingers, it is 375,000 joules. Now that's 375,000 joules. That's also known as 375 kilojoules. Okay. So we use this formula up here to determine the absolute kinetic energy of an object. Okay. When I say absolute, with reference to the Earth or something. Okay. But if we want to work out the change in kinetic energy, we use this formula over here. So change implies an initial and a final condition. Remember, delta is always equal to the final condition minus the initial condition. Now, the final velocity would be one which has the v in it, because remember, v stands for final velocity, and u is the initial velocity. So this would be kinetic final, and this would be kinetic initial. Okay? So we can use simply this formula here, half mv squared minus a half m, and this time the u squared, or you can, because both contain a half m, you can factorize that out and have a half m outside of v squared minus u squared. So it's up to you which one you use. I mostly use the top one because I'm too lazy to memorize the bottom one. So let's have a look at this question here. I will use the bottom one this time though. The 2-ton truck, now obviously mass must be in kilograms, so that's 2,000 kilograms, is travelling 100 kilometres per hour. When we look at that, we realise that it's a kilometres per hour. And then it slows to 80 kilometres per hour. Once again, we see kilometres per hour. And in doing so, it will change its kinetic energy. Now, what is causing this change in kinetic energy? It must be the brakes. So the brakes are doing work. Okay. So we'll interpret any signs like positive or negatives in a few more moments, but we'll just apply the formula. So before we go any further, we have to calculate 100 kilometres per hour into meters per second. So we multiply by 5/18. Remember, that's the secret number that does this really quickly for us. That's 100 times 5/18, and it equals 27.7. It's 20.77, so I might go to 27.8 meters per second there. And 80 kilometers per hour, doing the same thing, multiplied by 5/18 gives us 22.2. It's 22.2 repeated to be exact, but we'll just worry about that rounding later on. So the change in kinetic energy, which is work, remember work is changing kinetic energy, so calculating the work, would be a half times 2,000 times the final velocity. So the final velocity is 80, so that's the 22.2 squared minus 27.8 squared. That's the initial velocity there. And popping that into our calculator, whoops, that's a half times 2,000 times opening that bracket, 22.2 squared minus 27.8 squared is negative 280,000 joules, which is negative 280 kilojoules. Remember, kilo being 10 to the 3. Now, what does this negative imply here? This means that work is done against the motion. So we are slowing down. So the work done by the brakes would still be 280 kilojoules. Remember, we are interpreting this minus sign. So the work done by the brakes is 280 kilojoules, and it is against the motion. So it is, that's all that minus sign is there, is interpreted as. Okay. Gravitational potential energy. So just to define it one more time, gravitational potential energy is the energy an object has because it is somehow in a gravitational field. Now, every object on the surface of the Earth is in the Earth's gravitational field, and therefore, anytime I lift something, I give it more gravitational potential energy, and every time I drop something, it loses gravitational potential energy and it's converted back into kinetic. So I said a few moments ago how I got this formula. This formula comes from work equaling Fs. The force needed to lift something minimally is the weight force. So that is the weight force there. And the displacement is in the vertical direction. So this fellow here, he lifts it from here to there. That is a delta H. So it is delta H. So that's simply all that is. So when we see this formula over here, we just see W equals Fs. Right, now, we are going to talk about changes in gravitational potential energy because we add gravitational potential energy into a system or we lose it from a system. We're not going to say it has this exact gravitational potential energy at this point. So we're just going to use a change in H rather than H as a specific value. So let's have a look at our question over here. A 60 kilogram weightlifter holds a 50 kilogram barbell a half a meter from the floor. So it starts already at 0.5 meters. And then he's going to lift it to 90 centimeters above the floor. Now I'll go 0.9 meters. What's the increase in gravitational potential energy? You know it's going to be an increase because we're lifting it this way, okay, away from the center of the Earth, giving it more gravitational potential energy. If I was to do it the other way around, from 9 down to 5, I would lose gravitational potential energy and I would get a negative value. So that's what that would mean. Right, so let's apply the formula. So the gravitational potential energy is mg delta H. Now we've got two weights in this, that one and that one. This is the weight of the weightlifter. It has nothing to do with the barbell he is lifting. So it's the barbell that is actually getting the gravitational potential energy addition, not the weightlifter. The weightlifter is simply an object. It could have been a 120 kilogram weightlifter or it could be a 20 kilogram child doing this. It doesn't matter. Okay, so it's going to be the barbell's weight, which is 50 times 9.8 times the change in H. Now, delta H is always the final position minus the initial position, okay? So this will be, the final is 0.9 minus the initial is 0.5. Remember that delta is always final minus initial, otherwise you won't get the right signs coming out, the positives and the negatives. Popping that into our calculator now, it's 50 times 9.8 times, opening a bracket, 0.9 minus 0.5, and we get 196 joules of energy is needed to do that, and that means we've added 196 joules into the system. Okay, that concludes this little section. There is a worksheet now, which is worksheet 4C2 on energy using these two concepts. Thank you.